Hello, everyone, and welcome to the session. In the previous modules, we have spoken about deep learning primer, regularization techniques, and bunch of other things. And these are the concepts which you are listening for the very first time in your life, maybe. Very first time you are listening to these. So you might not remember these at the word go. As soon as you listen to this, you'll not be able to understand and remember. Right? We are not robots. We are not Rajnikants, right? Robo movie Rajnikant who will just scan the book and remember everything. We are not like that. Hence, I request you all to read mind map on a daily basis. This is the bare minimum that you can do. So go to 360digitmg.com, click on mind map. And here in the drop down, you have an option called AI and deep learning in the drop down. Select this option and it would open a mind map. Click on that. All you need to do is double click to collapse and double click to expand. Okay, that's how it works. Here we have spent some time on deep learning primer. We understood how a human brain usually works. What do we mean by compositionality? The initial layers in neural network. If this is your input layer, the initial layer captures low-level details. The next set of hidden layers capture mid-level features, and then the final set of hidden layers capture high-level details. And then you have the output layer. So you have input, output, and then hidden layers. Okay, this is how it works. Then you have artificial neuron, and every neuron will contain two components: integration component and activation component. We have also spent some time understanding the different optimization algorithms, which is used to reduce the loss or the cost. And now we clearly understand the difference between what is a loss function versus what is a cost function versus what is the error function. Then we have a lot of deep learning challenges and practical issues. We have spoken about those. How do we get rid of the collinearity problem? That is, if your inputs are correlated, you simply apply maybe principal component analysis and it would decorrelate the inputs. What do we mean by covariate shift? What are the various options that you have to choose for deciding the best neural network settings? Right? Number of hidden layers, number of neurons in each hidden layer, activation functions, error function or cost function, or loss function, rather this has to be changed, loss function. Gradient descent methods, which method do you want to use? What is the size of mini batch, number of iterations, number of epochs? Learning rate, again you have shrinking learning rate and fixed learning rate. Fixed learning rate has a challenge of bouncing around the ball. Hence, we have shrinking learning rate, which includes exponential, delayed exponential, bold driver, and step. Then you have weight initializations, wherein you have random initialization, Xavier's or Glorots, Heath initialization, normal distribution, uniform, so on and so forth. And you also have vanishing gradient problem or exploding gradient problem. Right, we spoke about that. We discussed about overfitting and how to avoid overfitting. We avoid overfitting using regularization techniques, and here are a bunch of those. Early stopping, you have error change criterion, weight change criterion, dropout, drop connect, weight decay, L1, L2, adding noise, then data transformation, batch normalization, shuffling the inputs, curriculum learning, data augmentation, bunch of those. And then we venture into running the first algorithm using PyTorch. But even before that, we have got introduced to a few of the PyTorch functions. And we have to proceed further from here. Before we proceed further, let me change the runtime type to GPU and I ran. Let me save this. And let us continue with this specific business problem. So we are going to work on energy prediction model. Energy prediction model. Okay, or we are going to work on rather this data set, not model, this data set. Okay, so the appliances energy prediction database or data set. It contains data pertaining to 4.5 months. 4.5 months of data is available. And this data is related to temperature and humidity measures. Okay, it is related to temperature and humidity measures for different rooms. And different rooms are in a low energy building. And you need to, given the temperature and humidity of all the various rooms in a specific building, you need to predict what will be the energy consumption. The first and foremost thing is we need to understand what are the various libraries that are needed. And we will have to import those. Okay, so let us, let me first import. Okay, I'll maintain different lines of code for your purpose. So you import the library. Say we are importing pandas. For the first time when you run, it is going to connect to the server, which is available. Hence, it's taking time. So it is initializing and it is connected. Then you open a different line of code. And you're reading the file. You're reading energy data complete dataset. And you're storing that in an object called data. Okay, and then within this dataset, it's in downloads folder, but it would obviously throw error because we need to have this on our Google Drive. So I'll click on this and then click on this option, which would mount the Google Drive. So I'll say connect to Google Drive. So the Google Drive is getting mounted. Only if your data is in Google Drive can you actually import that and then proceed further. Okay, because this is on cloud. It's not connected to your local machine. Okay, there we go. Let me refresh and see. Not yet. It's taking some more time. It has given a pop-up message that this might. Yep, there we go. We have the drive. Let me go to my drive. Let me see if there is something. Oh yeah, PyTorch. Okay, there are various files, but I doubt we have file of choice. Yep, here we go. Energy consumption data set is available. So I'll copy the path and paste it here. Okay, so let me close this. Now that we have the data set, we are going to read that using pandas. Pandas has a function called read_CSV. And within the double quotes, you give the complete path of the file along with the name of the file and the extension. and you're storing that in an object called data. And also it must be there in the downloads folder. So let me go there. Consumption. Yeah. Let me open this so that I might show you the data set. And you have data of various appliances, lights, the temperature, humidity, etc. Various other things like wind speed, visibility, etc. Anyways, our objective is to predict the overall energy consumption, but we also have a date column. This is not a forecasting problem. Okay, we are not applying our traditional forecasting techniques here. So this date column does not really make sense. Of course, you might counter me saying that, hey, if you know which country data this is from, based on the dates, I can figure out whether the data is from summer season or winter season, etc., or rainy season. So based on the dates or the month, you can figure out which season it is. And these seasons make probably more sense in predicting the electricity consumption. However, we are not doing that. We are just going to delete this, okay, because our focus is on understanding this use case by using PyTorch. Okay. But otherwise, I would strongly recommend you to convert this into seasons and then use seasons for future prediction purpose. Okay. So let me run this. And what we are doing is we are dropping this date column. We are saying go to the column date and drop it from this data and store it back to data. Now, if you see data.head, it will show you the initial 5 rows of the data set. And here the date column, which was supposedly the first column, is removed. Next. Also this adding. Then we have a few more lines of code. I'm just copying each line of code and then typing. Friends, however, see, I'm just explaining you what each line of code does, and I'm explaining you the concepts. Hence, I'm taking the luxury of copying and pasting the code here. However, when you practice, you will have to type it. Okay, I request you all to type each line of code. This is the only way to learn. If you just copy and paste like what I'm doing, and if you do not type the lines of code, then you are not going to learn Python programming in your entire life. You spend your lifetime and you'll not be able to learn. So instead type it, for example, columns. I'll go to data, I'll pick columns from this data set. I'll pick all the columns and I'm going to store it in columns, COLS, that is the object name. Then maybe I'm going to create another object called number of columns. And here I'm going to go to data and I'm going to say get numeric data. So the moment I start typing that, it shows me a pop-up. You just select that. Get numeric data columns. Get the columns where you have numbers. Do we have non-numbers? I doubt. We have non-numbers somewhere. No, we do not have. Everywhere we have numbers only. Okay, fine. And then you might say that, let me get a list of columns, and then I'm going to subtract the number of columns from that. If I were to run it, the answer says null. What does that mean? So the first line generates the list of columns in your data set, and the next line, you know, the columns that contain the numeric values are stored in this variable. When you subtract the numeric columns from the list of the columns, entire list of columns, it is possible to obtain those that are non-numeric. But do we have any non-numeric variables? No, everything is a numeric variable. Hence, you got an empty list. That means there are no categorical features. If you have categorical features, you might have to decide on whether you want to do some kind of encoding of that particular variable. So number of columns thing is done. Next. We're also going to look at this specific function wherein we are going to this data, and then we are checking whether we have any null values or not. And then we are going to add, we are going to use some function to find out whether there are any missing values in each and every column or not. And when we run it, you get to see that there are no missing values. We do not have any missing values in the data set. Then there are multiple ways of figuring out whether you have outliers or not. Friends, once again, I'm just going to copy these and paste. Okay, but you are not supposed to do that. You are supposed to type each line of code because you are learning. If you ask me a question on until when should I do that? My answer is until you get a job. Until you get a job, please keep typing, keep typing. Even if it is a simple line such as import pandas as PD, if you feel, oh my God, how many times do I run the same thing? Don't you worry, you keep typing. So here you have an empty object called outliers. Okay, and we're going with a specific rule, which is also a rule to identify outliers, and that is 3 standard deviation rule. You all would, I think you all are aware of normal distribution, and I'm sure you all are aware of 1 standard deviation, that is plus minus 1 standard deviation. Then you're also aware of, I'm sure, plus minus 2 standard deviation. In that way, you also have minus 3 standard deviation, plus 3 standard deviation. Okay, so these are a few things that we have. Now, what we are doing is we are writing a for loop. When you say data.shape, if you were to just run this, it would tell you, okay, even before that, if there's a value which falls outside 3 standard deviation, outside plus 3 standard deviation or minus 3 standard deviation, the values are considered to be outliers. This is also another rule alongside the rule which says, you know what, if you have a box plot, if the values fall outside these 2 values, then they're called as outliers, right? On similar lines, if the values fall beyond plus minus 3 standard deviation, then also they are called as outliers. So here we are saying data.shape. If I were to run this, why is that so? So just give me a minute, sorry. Okay, sorry. If I say data.shape, you have the number of rows and number of columns. This has an index number 0 and this has an index number 1. In Python, indexing starts from 0. When you say data.shape of 1, you're referring to columns. This is number of rows and this is number of columns. And colon. So you have written a for loop. You're saying for I in range of 28. Range of 28 means it will say 0, 1, 2, 3, 4, all the columns. Okay. All the columns is what you are interested in. And then here, since every column is a numeric value, you can identify outliers. So what we are doing next is, you're saying, go to the columns, okay, and then calculate the mean of that, minus 3 times of, go to the data of each column, calculate the standard deviation. So all you're doing is X bar, which is a mean, minus these 3 times of standard deviation. So from the mean, you're taking 3 standard deviations on this side. From the mean, you're in the next line of code, you're saying, go to every column. You're saying data shape of 1, so range of 28. So if I is 0, it will go to column 0, calculate the mean, minus 3 times of, go to column 0, calculate the standard deviation. Same is the case with this also. Go to column 0, that's the first column, calculate the mean, plus 3 times of, go to column 0 and calculate the standard deviation. So you get X bar plus 3 standard deviation. This would give you the minimum value. This would give you the maximum value. That is, this happens to be the minimum value. This happens to be the maximum value. Any value which falls beyond maximum value or minimum value would be called as outliers. Okay. So all you're saying is, I'm just starting an object called count equal to 0. Then I'm writing another for loop. I'm saying, do this for every value. Here you're doing it for every value. You're going to every column, every row of that column and calculating. And again, you're saying, once you get all the values, go to every column, look at every value. And if that value that you get is less than the minimum value or greater than maximum value, then you say count equal to, this is nothing but count equal to count plus 1. This is an abbreviated way of writing it. That means you're counting how many outliers you have. Take those number of outliers that you have and divide it by the total number of observations. If you have 10 outliers out of 100 observations, 10 by 100 would give you 10%. Okay, if you have whatever, say you have 100 outliers out of 19,735, you get some number. That is a percentage that we are interested in. That is a percentage that we are interested in. And you're taking that, you're saying go to outliers, go to every column and show me the percentage of outliers with 3 digits, 3 floating point, means 9.367. percentage, right? 3 digits. This is what you're doing. And finally, you're saying print out the outlier details. So by printing out this, you're going to look at list of all the features or all the columns along with the percentage of outliers. And remember this thumb rule that if you have less than 3% outliers, you might want to ignore them as a thumb rule. One second, sorry. Okay. So if I were to run this, you get all the outliers. Okay. We are still doing pre-processing. Remember, friends, that roughly 60% to 80% of your time would be spent in understanding the business problem, collecting the data, and preparing your data for the modeling phase. This is where you do all the heavy lifting. And just executing the algorithms is a walk in the park. Okay. All right. So here we have something called as data scaling. Although data does not need to be rescaled, you need not do that. If you do this, it may improve the accuracy of your model. Okay. If you have basically say number of children that you have, 1, 2, 3 in that way. And if you have age of a person, age will be 30, 40, whatever. So these two, number of children will have single digits mostly. Age will be 2 digits mostly. But there is a difference in the scale. If you ensure that both of these are of the same scale, then it will accelerate the training process. It will make the training process faster. And there are two main ways of standardizing. What are those two techniques of standardizing? One is called as normalization, which is also called as min-max scalar, which is also called as range method, because range is nothing but max minus min. So you take each value, subtract it from the minimum value, divided by the maximum value minus minimum value. This is normalization. Then you also have standardization. In standardization, you just do x minus mean of each value divided by standard deviation. So now what we shall do is, we shall take the variables, we are taking x and y, and what are we doing? We're saying that take all the rows and columns from 1 until the last column and store it in X. Take all the rows from the in data, go to index location, take all the rows, comma. After comma, give a space, friends. It will make this look much better. Okay. 0 means only the first column is what you want to take, and that happens to be your output variable. We don't know. Then, if you look at this data set, this appliances, this is your output variable, and rest all are input variables. Somewhere you have wind speed, which has probably 6, 5.5, so on and so forth. And somewhere else you have in 18s. Right? So given that there is such a huge difference among the various variables, we need to rescale the data. So you say x minus minimum value divided by max minus minimum value. And you're storing it in x. And then when you say x dot head, you get to see the top 5 rows of the data set. And now what do we need to do? We need to split the data. Now all the data pre-processing part is done. We are going to split the data. We are going to split the data into 3 parts. Say you want to have the training data. You want to have the validation data. You know what? Validation data is also called as development data. It's also called as dev set. Then you have test data set. And then there are multiple ways of splitting, but just remember, friends, if you have a huge data set, thousands and millions of rows, then we might want to split the data in this ratio. 98, 1%. 98% of data would be in training, another 1% in validation, another 1% in test. However, if you have a smaller data set, then usually you split the data in this ratio. 60% of the data would be in training, 20% in validation, another 20% in test. So that is what these further lines of code would do. Okay. You can look at the shape of the data set. Let me run this first. We have 19,735 rows and 27 columns. Now, if you want to split this in the ratio of 60, 20, 20, then you can write these lines of code. All you're saying is length of x. Okay, what would this length of x give you? It will tell you how many rows you have. You multiply it with 60%. And the moment you do that, you will get something in decimal format. But you're saying convert that into an integer. Into 60 means 60%. So 60% of data you want to have in training. And if you say 80%, 80% of data you want to put in development. So remember one thing, we are trying to split the data in the ratio of 60 in training, 20 in validation, another 20 in test. Done. Then we use a sample dataset. Using sample function. So using the sample function, we want to shuffle the elements or the values that you have in features and target matrices. Features means inputs, target means output. And by setting this fraction, you're saying what fraction of variables you want to shuffle. Because here, what are we doing? We're just saying that 60% I need in training, another 80% in test. But we nowhere have split the data randomly. Okay. So when you shuffle, when you say fraction equal to 1, x dot sample, all you're saying is shuffle all the elements and you store the references of how the data are shuffled in random state. Random state equal to 0. And you give some number, and in that number, you store the names of all the observations which are getting stored in different objects. Then we are using indexing to split the shuffled data. So now we have shuffled data here and here. And what you're saying is go to the shuffled data where all the observations are shuffled, rows are shuffled. Go to the index locations. Take all the rows from the start until train underscore n. So what would be there in train underscore n? Let's see. Print train underscore n. And then let us also print the underscore end. So 11,841 observations, part of training data. So you are saying that go from row number 0 until row number 11,841. Take all these rows and all the corresponding columns. Store it in x underscore train. Store all the other values in y underscore train. Then from 11,841 until 15,788, take all the rows and all the columns because you're taking it from X. So all the inputs would be there. Store it in this object X underscore there. Then take all those rows from 11,841 to 15,788 and store it in Y underscore dev because those are output variables. Then from 15,788 until the end of the data set, take all rows, all the columns, put it in test. And all the output columns from 15,788 until the end, store it in this. Let me run it. Done. Now you can also print to understand the shape of all the variables. So let us do one thing. Let us print the shape of inputs and outputs and see what happens. So you have 11,841 observations in your training data. Output of all those observations is available, 11,841. Then in development data, you have 3,947. All those observations and 27 columns are there in inputs, and in your output, you have 3,947 rows. Rows in output variable. Yes. Then for test data also, you have the shape. Of course, X means you also have inputs, multiple inputs. Y means you only have one. Now, this is one way of splitting, friends. If you feel that, hey, all this is big headache, I want to, use some inbuilt function to split the data, then sure, an easy way out is this part. From scikit-learn model selection, import train test split. Okay. Then what are we doing? We are saying, take this shuffled data. We already shuffled the data set here. Take that and ensure that you have 20% of the data in test. Another 80% will be part of train. So you split that into training and test. And you're saying, go to this test data and split it into half. Okay, so I think it'd be even better if I do it this way. Let me first run this. And let us do one thing here. So let's print the shape of x underscore new shape and y underscore. Let me print the shape. Let us also print the shape of x underscore test underscore 2, comma, y underscore test underscore 2. Uh-oh. My bad, sorry. That is what I was wondering. What happened? Everything is showing. Okay. So this is the split that you have. Now what you're doing is you're saying x underscore test of 2. Just a minute, sorry. Of 2 and shape of 0. See here, when you look at this line is giving this, and this line is giving this. Test x underscore test underscore 2 dot shape of 0. 0 means it will refer to this. 1 means it will refer to this. Divided by x underscore new dot shape of 0 would be giving this. So it'll be 3947 divided by this. And then when you divide that, you get some number. And you're saying that that percentage is what you want now. And now what are we doing? We are trying to split this again. This data set is again being split. So let me do this. These are all different ways of, doing it. Whichever technique you feel is apt. Whichever technique is apt, you run. So here, when you print this, we get 25%, right? So you're saying that you want 25%, that is 0.25, to be here in this. And this x underscore new shape, you are going to take 25% of that and put it into the next. I mean, you're just giving x underscore train underscore 2 and x underscore dev underscore 2, right? So let me copy and paste these values here. Okay. So we have this. Sorry. Always come on. So here you say dot shape. Yep, I think it should give me the results now. So you're taking 25%, which is when you divide 3,947 by this, you get 25%. And you're now splitting this data set, which has 15,788 observations, once again into training and development. And you have the shapes of that. So it ultimately becomes 11,841, 3,947 for training data set and development data set or validation. And for test also, it's the same. So either you do this or you do this, it means the same. Wherever you feel, or whichever way you feel is easier, you can opt that. Okay. What are the disadvantages if you don't prepare your data for analysis? I know data preparation is very time consuming, no doubt about that. However, if you fail to do that, what happens? If your data contains noise or missing values or redundant columns or irrelevant columns, then it is going to take a longer time to train. And in most cases, the delay is so long that it takes more time than the time that you spend in preparing the data. If 5 columns are irrelevant when you prepare your data, you can reduce the training time considerably. Okay. And if you don't prepare the data, if you have unclean data, usually it will lead to errors. You might have missing values. It will completely deviate your analysis. Okay, so these are the challenges. Then outliers and noisy data will not help your model work well on the future data. Suppose in your data set, there is a column called age, and there are, say, 20 people whose age is more than 100 years. If you include them as is, they will be outliers. More than 100 years someone has lived means that is an outlier. But then what happens is, if you do not remove them, your model will get trained on those outliers also. And your future data, obviously, you'll not have too many more than 100 years, right? Very less. So your model will get biased. It doesn't generalize well. Okay, so we need to avoid these things. Okay, hence data preparation is extremely important. Okay, now we need to build the deep learning model. Until now, did we build deep learning model, neural network using PyTorch? Not really. We have just done data pre-processing. Now we get into this. So I'll import the required libraries. You're going to import Torch. And within Torch, you have something called as NN, which is neural network module. We are loading that. Let it get loaded. Yeah. Why did it take slightly more time? Because that is invoking the GPUs. Next, we segregate the features from the target. Okay, so we are, for all these, we'll do the same thing. We know now very well that we need to convert the values into float point so that your error or loss functions are calculated. Here, what are we doing? We are taking all the training values, converting them to float, all the training values output, converting them to float, storing in different variables. Now you're going to define your neural network architecture using sequential container. And we are making sure that we have 4 different layers. So we are creating a 4-layer network. And we are using something called as ReLU, rectified linear unit. And for the first 3 layers, we are using ReLU. And for the last one, we are not using any activation function. Considering why are we not using any activation function? What did we discuss in the initial days? If the output variable is continuous or a numeric value, it becomes a regression problem. And when you have regression problem to deal with, you need not give any activation function in your output layer. So here what we are saying is go to this training data, shape of 1. I mean, 0 means number of rows, 1 means number of columns. And you're saying connect those with 100 neurons. And we want ReLU activation functions. Then in a linear fashion, linear means sequential, by the way. Okay, we are saying connect these 100. So if you say x underscore train dot shape, you get 11847 rows, 27 columns. So you're saying 27. If you have 27 columns, 27 inputs, then you'll have 27 neurons. Then you're connecting those to 100 neurons. Linear means it will connect every neuron to every neuron. Then you want ReLU activation functions in all these neurons. Then you are connecting these 100 to another 50. And in every neuron, you're going to have ReLU activation function. And these 50 are connected to another 25. And each and every neuron once again contains ReLU activation function. And these 25 are connected to a single neuron, since the output variable is numerical, continuous. Okay, this is the network which we are creating. So nn.sequential, done. After this, we need to mention that we need a loss function. Here we are taking mean squared error as a loss function. Torch.nn is neural network module, and mean squared error is a loss function. Yeah, this is what we have spoken, we have discussed umpteen number of times. Let's let me go to documents here. And yep. If you have output variable continuous, or for that case numerical, you're going to have mean squared error, or any of these can be used as your loss functions or cost functions, which are used for optimization purpose. And that is exactly what we are having here. And then you have optimizer. We already have discussed about optimizer. Okay, and then we have Adam as an optimizer that we're using. Adam has how many parameters? If you remember, 2 parameters, beta 1 and beta 2. Okay, and you're giving a learning rate value as 0.001. And then we define the optimizer. That's it. Now we need to run the number of epochs, right? So we are going to create a for loop, and range of 1,000 means we want 1,000 iterations. We want to build the model on the training data, and we want to squeeze the results and store it in predictions. So what do you mean by squeeze the results? So it will take all the predictions, and suppose the output variable here, the prediction results, would be showing as 3,000 by 1, just as an example. That means you have 3,000 rows, 1 column, all the output values. You're just converting that into a single dimension. 3,000 multiplied by 1 will be 3,000. So that is called as squeeze. This squeeze function is used to remove the additional dimension in your this and then put it as single. Why is this important? This is important because your training data has single dimension. Here, if your output has 2 dimensions, it will throw error. It will say I'm unable to, compare 2 dimensions with 1 dimension. So you're ensuring that you convert this into 1 dimension. Okay, so you have all the loss values. And then you're saying you want to run all those iterations. And here what you're doing is, if at all, okay, anyways, optimizer, you're taking all the, you know, gradient values. You're doing a back propagation to minimize the loss. And then you're taking the next step in the optimizer. Meaning, if you have a loss function like that, initially you're not having any gradient. Okay, so randomly it is initialized. Next, through back propagation, you're going to update the weights. The weight is here randomly initialized, you update the weights. And when you update the weights, this optimizer will ensure that you move to the next step. Then you update the weights, then you move to the next step. And here you're saying that if this I value that you have, when you divide it by 100, if you get 0, then print the results onto the screen, the loss value. If the I value is say 99 divided by 100, is the remainder 0? No. If you divide it by 100, is the remainder 0? No. So it will not show the results of that. And the range starts from 0 onwards. 0, right? 1, 2, 3 until 999. So 0 divided by 100, remainder is 0. So it will give you some initial loss. Then eventually when it comes to I equal to 1, 2, 3, 4, 5, 6, 100, 100 divided by 100, remainder is 0. So it will again print the results for 100th iteration. Then 101, 102, 103, etc. And then at 200, 200 divided by 100 will give a remainder of 0. So again for 200, it will print the loss, so on and so forth. So let me run this. And look at how speed it is. 100 epochs, it is just printing in 1 second. Okay, now that we build the model, let us see how good or bad our model is. So all we are going to do here is, we are going to go to the model and we are going to use our model to test on the first observation of test data. And you get the predicted values. So let me store the predicted values. What is the predicted value? Let's see. Okay, you're getting 72.24. Now what you can do is, you can say that ground truth means actual value. You're saying, let me go to the output variable, the observation 0, let me get the item. And from predicted value, let me get the item. And let me compare those two. So it says ground truth is 60 and predicted value is so much. Of course, there is some error, but yeah, this is what you could do. All right, so we could successfully complete PyTorch code when it comes to ANN or NLP. In the AI training, AI and deep learning training, of course, you learn about what would happen when output variable is continuous, discrete in 2 categories. When your output variable is discrete in more than 2 categories, what happens? Everything is known. Okay. And when you have less amount of data, how do we deal with that? That is also another aspect which is addressed, explained as part of your training. It will be explained rather. For us, for certificate program in data science, this is good enough, this information. But we also need to get into the next variant, which is CNN variant. Okay, we need to also talk about CNN, convolutional neural network. Okay, So we'll get into CNN. First, we will talk about theory, and then we'll get into the practical aspect of it. Once again, I'll quickly show you TensorFlow, Keras, piece of code, and then we shall also run on PyTorch. So now it's 11:10. Let us take a quick break and then come back. So I'll pause the recording until then. So welcome to convolutional neural network or convolution neural network. CNN is a special case of neural network, which is used in handling images whenever you have images to deal with. And there are a lot of use cases in which convolutional neural networks has been used. We will talk about a few of these now. But majorly, it is used in detecting cancer in patients, for example, by looking at radiology images or pathology images or DICOM images or X-ray images, etc., figuring out what problem the human has. And another very good use case is with respect to self-driving cars. Okay, in that scenario also, CNNs are very heavily used. And CNNs are extremely ideal when it comes to dealing with image data. Typically, they are used in image classification, but there are also other image processing applications where CNNs are used. And as part of your professional certificate program in data science and AI, you have deep learning and AI training, right? In that, you'll also learn about OpenCV. Here, CV stands for computer vision. Computer vision. And when you do typical image processing, we use OpenCV, which is a library to handle images. Ultimately, that is executed in Python only at the end of the day. But for our discussion now, we are going to spend on CNN strictly. So the convolutional neural networks or neural networks as a whole became famous through ImageNet competitions. Actual ImageNet dataset contains 1.5 million images and 22,000 categories. But for this ImageNet competition, people have given away 1.5 million images and they were 1,000 categories. Given an image, the algorithm was supposed to give a name to that image. So we have animals such as bird, fish, mammal, etc. We have plants, tree, flower, etc. Right? So these are all the various categories. And given 1.4 million images and 1,000 classes, given an image, you need to classify on what is contained in that image. And in 2010, it started. In 2011, 2012, 2013, 2014, so on and so forth, this ILS VRC, ImageNet Large Scale Visual Recognition Challenge started. And in 2011, there was a guy by name, or 2012 rather, there was a guy by name Alex Krzyzewski. He and his team have experimented with neural network algorithms. And since then, every neural network, every ImageNet competition was won by those people who resorted to neural networks. Okay, and before that, people were using traditional machine learning algorithms. They were trying to extract the features from the images in a manual manner. And ImageNet is used, convolutional neural networks is used in solving a lot of business problems. One business problem is image detection. What happens in detection is your task is supposed to perform something called as object localization. Localization. Okay, on all the objects which are there in the image, and the output of all these localizations would consist of bounding boxes. You'll have multiple bounding boxes and you'll have multiple labels. And you'll have one label per box, such as this is a car, this is a dog, this is a person, horse, etc. So this task is used in self-driving cars also. And the objective is to, in the self-driving cars, the objective is to be able to locate the traffic sign, maybe road, and the road markings. Road will be having these kind of markings, right? These markings, right? You need to be able to figure out that. You need to be able to figure out what are the other cars, other vehicles. You might want to figure out pedestrians and many more. So your goal will be to detect the various objects. And the main purpose of localization is to generate bounding boxes that describes the object's location in the image. So output will have again the bounding box and the class label. It is used in sensors, this particular task in sensors usually, right? And it will be able to recognize whether an object is to the left or the right of the vehicle. If it's self-driving car, it will have a lot of sensors. Is a vehicle towards the left or towards the right? So those kind of things can be identified. Then we also have image segmentation. The task here is to output both the label. So for example, this is a road, this is a person in that way. So it will give you a class label, and it is going to give an outline of each object. So humans are given, persons are given different color, road is given a different color, tree is given a different color, building is given a different color, so on and so forth. If you have a radiology image, and if you want to figure out whether you have a tumor or not, whether it is cancerous or not, for instance, if I go to downwards, let me go to radiology images. Save radiology images. Then there's an image. It will exactly locate this image where we have tumor. Okay, it is going to exactly tell you where where we have tumor. All right. So it might say that, okay, let me put a mark over here. Maybe this region indicates that there is tumor, or maybe there is microcalcification. So these are the regions which have tumor, and it's going to give it some kind of a color code for you to easily, segment on where the problem exists. Then, of course, in self-driving cars, it will be able to figure out where is a car, where is a pedestrian, where is a guy cycling, right? The signages, etc. It will be able to help you recognize the different alphabets of different languages. right? Signages, all these you will learn as part of, at least with respect to the self-driving cars, you'll understand how to identify the lane marking, how to recognize the traffic signs automatically using convolution, using computer vision, all that we are going to do. Then CNN is everywhere. It is used to even classify, right? For classification purpose. That means given the image of a person, classify on who that person is. Tell me exactly who that person is. Be it whale recognition problem or putting a map or putting color code on top of the map to help you understand what are the regions where you have routes, etc. It is used for image captioning. Given an image, it would give you a caption. Two dogs play in the grass, a person riding a motorcycle on the dirt road. So in that way, it's going to give you captions for images. Okay, now the million-dollar question is, right? Why can't I use multi-layered perceptron or artificial neural network? Why shouldn't I do that? And let us see why we should not use. There is a specific data set called a Cypher-10 data set. Cypher-10 data set. This is an established computer vision data set, means people have manually collected the data, and it has 80 million images, or it is a subset of 80 million images, sorry. It has 60,000 images of size 32 by 32, and it contains 10 classes. That means for each class, you have 6,000 images. 6,000 into 10 would be 60,000. You have 32 into 32 color images. Color images, so it will be 32 number of, that is the width, 32 is the height, 3 is the color channels. So even if you have a single fully connected network, that means 32 by 32 by 3, you'll have 3072 neurons. And even if it is connected to a single neuron, you'll have 3072 connections. 3072 different weights is what your model is supposed to learn. Okay, 32 by 32 means if you have an image like this, you'll have 32 pixels here and 32 pixels here, meaning 32 pixels like this, 32 rows, and you'll also have 32 columns. And why 32 by 32 by 3? 3 means it's a color image. Red, green, and blue, RGB. So that's a color image. Okay. Now, if I have a 200 by 200 image, and if it's a color image, you'll have 200 by 200 by 3, which is, if you multiply these three, 200 by 200 is 40,000. 40,000 into 3 is 120,000. 120,000 weights. 200 by 200 is also considered to be a very small image. Usually in the cameras that you have, mobile phones, you will at least have, say, 10 megapixel camera. 10 megapixel means 10 into 10 raised to the power 6. Even if you have 1 megapixel camera available on your smartphone, that means 1 into 10 raised to the power 6. So it is nothing but 1 million pixels. If you have 1 megapixel camera available with you, then the dimension of your image will be 1 million by 1 million. Okay, and if it's a color image, what you do is 1 million multiplied by 1 million multiplied by 3. These are the number of neurons that you're going to have. Huge number of neurons, right? These are the number of neurons that you're going to have. And these many weights have to be learned. If these many weights have to be learned, then it's going to be a very, very costly affair. And one more thing is, this neural network architecture, such a neural network architecture that is NLP, does not take into account the spatial structure of data, meaning it treats every pixel as same, whether it is far apart or close together. If you have an image like this, maybe one person is standing somewhere very far away, and maybe another person is very close, and this is a road. Whether you pick up a pixel from here or whether you pick up a pixel from here, it will treat these pixel values as the same. You take all the pixels. Whether you take a pixel value here or here, doesn't matter. It is going to consider a tool like NLP, because if you have, say, whatever, 1000 by 1000, then you create 1000 by 1000 by 3, those many number of neurons. In this, when you give inputs, every neuron is considered to be equally good. Every neuron is considered to be the same. Okay. And if you connect every neuron to this, then it's clear wastage of resources and huge number of parameters, huge number of weights your model has to learn. And that way your model is going to also overfit. While only this portion of the image can be learned and this portion of the image can be learned, if you are learning each and every pixel, then you are kind of overfitting your model. So these are the various challenges pertaining to NLP. One is whether an image or a person is far away or close, it will treat them as the same. Whether you have, okay, and every pixel is treated equally, so you'll have far number of parameters. So I'm going to write it down here. What are the challenges? Number one challenge is far too many parameters to be learned. Number of parameters are large, very large. Second, every pixel, whether it is far or close, is treated equally. And if you are going to make use of every pixel, then you're considering every each and every pixel value if you have 200 by 200, now also, okay. Now I'll be talking, just let me know whether my voice is audible or not. Okay, now, not sure. All I'm saying is every pixel run okay. So I'll be talking, just confirm friends. That's my resume the record. So we have parameter explosion with MLPs. You know, that's the disadvantage. And hence we need to solve that. So these are the various disadvantages, right? Number of parameters are large. Every pixel, either it is far or close, is treated equally. And that means you're wasting your compute. This is the reason why people came up with another network, which is called as convolutional neural network. And here is where we need to spend some time and understand more. When you feed your images into CNN, you do not require to do much pre-processing. The way we have done pre-processing on the structured data set, when we have discussed about energy consumption, we have done a lot of pre-processing. Such pre-processing is not needed here. Okay, so images are usually fed as is. And the most common changes includes reducing the size of the image, that is called as downsizing. And there is also something called as normalizing. Okay, there are two pre-processing steps you perform. Let me talk about those right away. There are two data pre-processing steps which are performed. One happens to be normalizing. And another happens to be downsizing of images. Usually when you look at an image, obviously images contain pixels, and each pixel value has numbers from 0 to 255, wherein 0 means black color and 255 means white color. And in between these, you will have certain grayscale images. But then, if you have a color image, like RGB, red, green, and blue, RGB images or color images, when you process these, you need to segregate the 3 color channels as red channel, green channel, and blue channel. You ideally need to segregate these. And when you segregate these color channels as red, green, and blue, each color channel will look as if it is grayscale image. Each color channel will look as if it's a grayscaled image. So that means it is as good as treating each channel as a grayscale image, and the same logic applies. Each pixel value ranges from 0 to 255. 0 means black, 255 means white. Now, when you do normalizing, you take these values which lie in the range of 0 to 255, any value in between, and then you divide each value by 255. When you divide this by 255 and when you divide this by 255, 0 by this would actually give you 0, 255 by 255 will actually give you 1. So the values range fall in the range of 0 to 1. Not just this, there are a lot of other techniques which are used to normalize the images. And one of those techniques is called as mean centering technique. So it's up to you on which technique you might want to use. But the point here is, if you normalize the data, it is going to speed up the learning process. The training process will be fast. So training process will be fast. And it is also going to help you improve the performance. Performance means speed. So the speed increases. There is also another technique called as downsizing. That means you reduce both the width and the height of the image. This will speed up the learning process or the training process. We need to speed up the training process. Okay, so suppose this is an image that we have. Let me now remove the, and on this specific image, you apply something called as a filter. This is like a hidden layer. For example, if your image has size 5 by 5, meaning you have 5 rows and 5 columns. 5 by 5 means you'll have 25 neurons in the input layer. And say you're creating one hidden layer, and this hidden layer, when it comes to convolutional neural network, is given a special name called as filter or kernel or mask. All these three mean the same. And if you have, I mean, you are free to choose how many ever neurons you want, right? Number of hidden layers and number of neurons in the hidden layers is hyperparameter. It is a hyperparameter, right? So you're choosing, say, 3 by 3. 3 by 3 means 9. And in these, there'll be certain numbers. Initially, those numbers are randomly selected. All those weights are randomly initialized. Later on, through back propagation, the weights are updated. And say the final weights happen to be 101, 010, 101, just for our calculation purpose, okay? Say you normalize this image to, pixel values range from 0 to 255, but you have normalized the values into the range of 0 to 1, assume. When you apply this filter on this patch, it will be 1 into 1 plus 1 into 0 plus 1 into 1 plus 0 into 0 plus 1 into 1 plus 1 into 0 plus 0 into 1 plus 0 into 0 plus 1 into 1. When you do that calculation, you get a number 4. That number 4 is related to this central pixel. And that is a 4 that you observe here. Then you stride this filter one step at a time. When you say stride equal to 1, you move this filter by 1 pixel towards the left. So it was earlier here. Now we are moving it to this location. Again, you apply the same filter. So 1 into 1 plus 1 into 0 plus 0 into 1 plus 1 into 0 plus 1 into 1 plus 1 into 0 plus 0 into 1 plus 1 into 0 plus 1 into 1. When you solve that, you get another number. Whatever number you get, that would be giving this central pixel. For this patch, you get this central pixel value. Okay. So whatever number you get here, you put it there. Okay. Just to repeat, say you have chosen a filter. Filter has 2 names. Filter is also called as kernel or mask. This is like a hidden layer. And the values within this filter are determined based on back propagation. So if you have a 5 by 5 image, you have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5 by 5 image means 25. And say you are applying a filter, which is like a hidden layer of size 3 by 3. Means you'll have 9 neurons, 3 by 3, 3 multiplied by 3. And say you have done a forward pass and backward pass and updated all the weights. And the weights which you got finally were 1, 0, 1, 0, 1, 0, 0, 0, 1. When you apply this on this patch, you don't apply it on the complete image. You apply it on patches of the images. If you apply it on this patch, then simple math calculation. 1 into 1 is 1 plus 1 into 0 is 0 plus 1 into 1 is 1 plus 0 into 0 is 0 plus 1 into 1 is 1 plus 1 into 0 is 0 plus 0 into 0 is 0 plus 0 into 0 is 0 plus 1 into 1 is 1. 1, 2, 3, 4. When you add it, it is a simple summation, you get 4. Whenever you do this calculation, the number that you get would be considered as a number for the central pixel. So the central pixel here, value would be given as 4. Now, you take this filter or kernel or mask and you stride it by 1 step, meaning you move this filter by 1 step, 1 pixel towards the 1 pixel towards this direction. So you then, since you're moving it by 1 pixel, you move it like this. And do the same operation on this patch. Same numbers, multiply it with 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, do that. And then you get some number. That number belongs to the central pixel here. That would be this one. Okay. Then on similar lines, you stride it by 1. So you now move it to this. Here. Do the same operation. 1 into 1 plus 0 into 0 plus 1 into 0 plus 0 into 1 plus 1 into 1 plus 0 into 0 plus 0 into 1 plus 0 into 1 plus 1 into 1. When you solve it, you get some number that happens to be the central pixel. And then that is going to be here. Now, if I stride it by pixel equal to 1, further, it cannot be applied here. You cannot apply it here. Why? Because you don't have any pixel values here. So for this, you will not get any value there. These are called as border pixels. You will not get any value for the border pixel. And hence, when you say stride equal to 1, then you move to this direction. You apply on this patch. Then stride it by 1, move to this patch. Then again stride it by 1, move to this patch. Do the calculation, calculate the central pixel. Keep filling the table like that. Then move it by 1 pixel here. Stride it by 1. Stride it by 1. And then it stops because the entire image is now processed. Like you have addition, subtraction, deletion, you have convolution. That is some math operation. Okay. And these filters or kernels or masks are expected to always be of odd number. 1 by 1, 3 by 3, 5 by 5, 7 by 7. Otherwise, what will happen is you'll not come to know what is the central pixel value. Always, you need to provide odd numbers for your filter size. Okay. So this is how you continue the operation. So you apply on this patch, you get 3. You move that kernel or filter to this patch, you get 4. This patch, do the calculation, you get 2. 2 is this central pixel value. Okay. Then again, move it like this, you get the central pixel value as 4. Move it like this, then you get the central value pixel as 3. Stride it like this, then you get the central pixel value as 2. Stride it, then the central pixel value will be 3. Stride it, then the central pixel value will be 4. And then the size of your output, this is your input image, this is your output image, right? And you have a filter or a kernel or a mask. The output that you get is also called as convolved feature. or this is also called as a feature map, or a response map. Okay, next. So if you have an image of size 32 by 32, width 32, height 32, and 3 is the color. If it's a color image, you say 3, red, green, blue. But then when you apply a filter of size, say 5 by 5, even if you don't give this 3, it will automatically take 3. And the 3 is sometimes also called as depth. The 3 color channels, sometimes it is also called as depth. Okay, so you have height, width, and depth. So you take this filter, you apply this filter on all the patches. In that way, keep convolving it throughout, and then apply it on all the patches. And finally, you get the output. That output that you're going to get would be of size 28 by 28 by 1. Please remember that when you apply this here, okay, let me go back to this. The size of your input image is 5 by 5. So your input image size is 5 by 5. And your filter size is 3 by 3. Filter size is 3 by 3. When you convolve this on this, you get this pixel. So the border pixels are gone. You cannot get those, because to get those, you need to extend this like this. Maybe you want to extend this like this. Only then you get this central pixel. But we cannot extend like that because we need pixel values here, 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 and here, but we don't have those. Hence, the output that you get is of size 3 by 3. Because these border pixels, these, and these, you don't get any values. So all you get is for the central pixels, right? One, all for all these. So you have those, and those are coming out here. In that way, the output image dimension reduces. Okay, when a filter is convolved on the image, the output size changes. Okay, so when you apply a 5 by 5 filter, the formula is like this. N minus F divided by stride plus 1, where N is the size of your input image. So you have 32 by 32. So N will be 32. You're applying a filter of size 5 by 5. So F value will be 5. Usually stride equal to 1. For this example also, stride equal to 1 plus 1. So you get 27 by 1, which is 27, plus 1 is 28. So you get an image which is of size 28 by 28 by 1. That's what you get, okay? Because you're applying one filter. If you apply one filter, the size of this will be 1. And when you apply your filter on an image, your output would be some feature that your filter is going to extract from your image. But what is that filter? No one knows. So it is black box. So the activation map or feature map or response map all mean the same. Okay, next. If you are going to apply another filter of size 5 by 5 on this, so this filter will get convolved on the entire image, the way we have seen in the previous slides, and then it is going to extract some features from the image. Those features you will not come to know because it is black box. Manually, if you extract, you can say these are pixel intensity values, these are color values, etc. But when it is automatically done, you will not come to know on what features are extracted. So again, the output size will be 28 by 28 by 1. Formula is again the same. N minus F divided by stride plus 1. If you apply 6 filters of size 5 by 5, so if the input image is 33 by 33, 32 by 32 by 3, even if you don't mention that this has to be 5 by 5 by 3, it will automatically take 3 because it's a color image. And if you're going to apply 6 such filters, the output size will be 28 by 28 by 6. Why 6? Because you applied 6 filters. Next, if you apply another hidden layer or another convolution layer, and if you say that the size of that would be again 5 by 5, if you mention only as 5 by 5, what it does is automatically it will say 5 by 5 by 6. Why? Because the size is 6 here. Here, if you give a filter size of 5 by 5, it will automatically take 3 because here the size is 3. Obviously, I mean, you will be able to calculate, but if you have a 28 by 28 image, n minus f divided by, if stride equal to 1, if you have a 28 by 28 image, n is 28. Filter size is 5 by 5 minus 5 divided by, say, stride equal to 1 plus 1. So the output of this, when you apply a 5 by 5 filter on this, then the output would be 24 by 24. It will be 23 by 1, 23 plus 1 is 24. In that way, right? And say you're applying 10 5 by 5 filters, convolution filters, then the output will be 24 by 24 by 10. Since you're applying 6 filters, you get 6. Only in the input layer, if it is a color image, you'll have 3. If you have a grayscale black and white image, you'll have 1. So if you have a color image, you'll have 3 as depth. If you have a grayscale or a black and white image, then this value will be equivalent to 1. Right? If you have, say, for example, 28 filters here, instead of 6, if you have 28, it'll be 28 by 28 by 28. Each filter that you're applying is going to extract some features from your image. Each filter that you apply is going to extract certain features. What features your model is going to extract is not known to us. It is black box. Okay, now, suppose you have an image which you're supplying it to your convolution neural network. What your convolution neural network does is it is going to extract the features. So your convolution layer, then you are using ReLU activation function, conv ReLU pool, conv ReLU pool, conv ReLU pool. Convolution layer is nothing but a hidden layer. How many such convolution layers do you want to have is up to you. What activation function you want to use is up to you. But this is an industry standard. Con, relu, pool, con, relu, con. I mean, this is how people use convolution layers with pooling layers. And the place where your convolution layers end, there you'll get all the inputs or features which were extracted from your data. All the features which were extracted from the image would be there at the end. Those features, you supply it to your fully connected network or multi-layered perceptron or dense network, whatever you want to name it. The moment you supply all these features to this, it is going to immediately classify and tell you what this image is. So it's saying that, I mean, these green lines are like probability values. And for car, we are getting highest probability. Hence, it says that this is a car. Okay. That is how you build your model. But there are a few more things that we need to talk about. But then one of our friend has some question. I didn't quite understand what that question is. Yeah, Vipin.
It is true that when you are taking image,
sorry,
it is always...
I'm unable to hear you. Sorry, one second. Yeah, can you talk now?
Yeah. Am I audible, sir?
Yeah, you are audible, Vipin.
Yeah, sir, this question is related to that when we are talking about the image and using this image to pass to the filter to create an artificial intelligence, like a car is using artificial intelligence knowledge that is something is color is coming, so it is driving by auto mode. In case if we are in a 3D image, if the robots are sitting inside and can assess the depth also, because you are assessing out a 2-dimension figure in this case.
Okay. Okay.
So my question is related to the future aspect of 3-dimensional. When we are working in the space, same principle will be applied for the future artificial intelligence?
Exactly. Exactly. Right? Even for a 3-dimensional image, you do the same thing. You take the image, whatever filter you are going to apply, it will consume the entire thing, including the depth.
Yes. In your case, you are using the color and dimensions is a 2D. The metric is 2-dimensional. Like initially use 32 by 32 into 3, and 3 is the color, green, blue, yellow, or whatever the color is. But when we are working in the production field, for example, we are working in the some units that are manufacturing something, so they have to analyze with the third dimensions also, which is not visible by the image.
Give me one use case. Can you give me one use case?
Okay, I'm in the, for example, I'm producing the composites. It is the length, width, and dimension. I'm calculating the length and width always, but thickness is having variation. So this thickness will not be color image in this code. So that third dimension is that having a density, which if it is, we are not considering the thickness property, the variation will come throughout the density variation. So this is kind of a sample which is property related to third dimension. It is not the density, any mechanical property, like physical or mechanical, which we have to optimize through artificial intelligence. Otherwise, whatever I have to do, I have to drag the sample and feed it to the UTM machine and get the value. But if I use artificial intelligence, because you are giving me the concept to use this information in production line. So I have to work with the robotic field. So these robots also have to see that dimension which is not coming from this image, which is you are giving me 2 dimensions, but that third dimension, which is very important for production line. So this I am using pure information in my science, in my study. So this is came in my mind, and I raised the question in open platform. Otherwise, it may be the vague question that you know what.
No. It is a very, very interesting and very, very important question that you have raised. Of course, we'll do one thing, Vipin. Let me talk about this tomorrow, because tomorrow also we will be having a session. I'll not be able to complete this today, but then tomorrow certainly I'll take this up, because analyzing 3D images has slight change. in comparison to analyzing 2D images. So I'll talk about it more, right? Tomorrow in the session, I'll talk more about it. Yeah. Makes sense. You have a very, I mean, that's a very valid question that you explained. Yeah. Let me continue. Yeah. Thank you. Okay. Say you have a 7x7 image. Okay. And say you have a filter of size 3x3. Then you take that 3x3 filter and convolve it on this particular image, 3x3. Then what you do is you stride it by 1. Stride it by 1 means you skip 1 pixel. Stride it by 1, stride it by 1. Okay, you continue in this way. How many times could you stride? 1, 2, 3, 4, 5 times. Okay, and ultimately, if you could stride this way 5 times, you can also stride in this direction 5 times. So you'll get an image which is of size 5x5. And then if you stride it by 2, then what happens? What you do is you skip it by 2 pixels. Skip it by 2 pixels. So you could only stride 3 times. 1, this is 1, 2, 3. That's it. Hence the output size would be 3x3. But if I say stride equal to 3, would it even be able to move? No, you cannot move. Stride equal to 3 means, because stride equal to 3 means skip 3 pixels, go here. But here you cannot move, because in order to move that way, you need 2 more pixels here. You're unable to. So it doesn't fit. It cannot apply a 3x3 filter on a 7x7 input image. Okay, if you use stride 3, you cannot move. Hence, we have this formula n minus f by stride plus 1, which we have already discussed. When you divide it, if you get an integer, that means you can apply those strides. If you get a float value, decimal value, float value, then that stride cannot be applied on the image. This is yet another thumb rule. There is also something called as padding. Okay. And a very common practice is to zero pad the border. If you have a 7x7 image, that means 1, 2, 3, 4, 5, 6, 7 pixels here, and 1, 2, 3, 4, 5, 6, 7 pixels here. It's a 7x7 image. If you pad it by 1 pixel, what will happen is you add 1 pixel here, 1 pixel here, 1 pixel here, 1 pixel here. When you do that, 1, 2, 3, 4, 5, 6, 7, 8, 9. You will have 9 along this. 1, 2, 3, 4, 5, 6, 7, and you'll have 2. So you'll have 9 along this. So you're having a 9x9 pixel now. Okay. Then if you take a 3x3 filter and stride it by 1, what will be the dimension? So now the n value has become 9, 9x9. Filter size is still 3x3, so it is 3. Stride equal to 1. So n minus f, 9 minus 3, divided by stride equal to 1 plus 1. So you get 6 plus 1, which is 7. So you're getting a 7x7 pixel. Sorry, the output image is 7x7. There's also one more formula that you all might want to remember. And that formula is, if you want to ensure that, say you have a 7x7 image, you also want your output to be 7x7. Then I should do padding with how many pixels? Padding with 1 pixel or 2 pixel, etc. This completely depends on your filter size. If your filter size is 3, say your output, you want an output of 7 by 7. We are kind of doing reverse engineering here. And then say you have a filter of size 3 by 3. If you have a filter of 3 by 3, output is 7 by 7. Now the question is, okay, input image is also 7 by 7. The question is, by using how many pixels should I do padding? If you pad it by 1 pixel, then what will happen, right? So to understand how much padding you need to do, there is a formula called as f minus 1 by 2. If the filter is 3 by 3, 3 minus 1 by 2, right? 3 minus 1 is 2. 2 by 2 equal to 1. So you need to do padding with 1 pixel. Say a filter size is 5 by 5. Then the amount of padding should be equivalent to f is 5 minus 1 by 2. So you get 4 by 2, which is 2. So you do padding by 2 pixels. Here, if you get a 7 by 7 filter, then this will become 7 minus 1 by 2, which is equivalent to 6 by 2, which is 3. So you do a padding by 3 pixels. So that's another thing. So let us understand this aspect also. Say you have a 32 by 32 by 3 image, and you are applying 10 5 by 5 filters with stride equal to 1 and padding equal to 2. In that case, what will be the size of the output image? So input image is of size 32 by 32. And you're doing padding by 2. Means you're adding 2 pixels surround. Pixels around. So you're adding 2 pixels here, 2 pixels here, right? You're adding 2 pixels here, 2 pixels there. So the new dimension would become 32, 33, 34, 35, 36. So it will become 36 here. Here you have 32 pixels, then 33, 34, 35, 36. So you'll have 36 pixels here as well. So you have a 36 by 36 image. Now if you take, so that means n by n equal to 36 by 36. Filter size f by f is still the same, 5 by 5. And what is the formula to get the output image? N minus f divided by stride plus 1. N is 36. F is 5. Stride is 1 plus 1. So you get 31 plus 1 is 32. So you get output 32 by 32 by, since you have 10 filters, you'll have 10. That's how you calculate. Now, there is another question. If you have an input image of size 32 by 32 by 3, and if you have 10 5 by 5 filters, if you're striding by 1, pad 2, what will happen? If you pad it by 2, just now we understood that you'll get a size 36 by 36 by 3. So that's your image, 36 by 36 by 3. And then you are applying, say, one 5 by 5 filter. 5 by 5 means you'll have 25. And to help you answer this, Okay, let me, okay, there are two things that I need to explain. First of all, I need to have our dear friend unmute. Yeah, Fahim, can you please unmute yourself?
Yes, sir.
Yeah, what part you did not understand?
Yeah. Actually, just previous slide, just only you give the padding and the calculation is 36. So just I could not understand the calculation about the with the help of padding how is happen the 36.
Well, let's take a very small example in that case if you did not understand.
Yeah.
Okay. How many rows and columns? What is the dimension of this image that I've just drawn?
5 into 5, sir.
Wonderful. If I pad it by 1,
Yeah.
means what? What do you mean by padding equal to 1? If I pad this image with 1, what will happen?
Sir, it will it will count it the extra one
That
pixel.
means around this image,
Yes.
around this image, around this image, I'm adding how many pixels each? 1 pixel.
Yes.
You're with me, right, Fahim?
Yes. It will happen.
5 by 5 image.
Yes.
If I add 1 pixel here, 1 pixel here,
Yeah,
5 plus
it
1
will be
is
6 by
6.
6. Yeah, it
Why
will be
6
6
by
by
6?
6.
Why 6 by 6, Fahim?
Because now with the help of
I'm
padding,
adding 1 pixel on this side, 1 pixel on this side. So total 2 pixels I'm adding, right?
yes.
5 plus 2 is what?
5 plus 2, 7.
Then how? Why are you saying 6? Tell me.
Okay, I understand. I was calculating all the
Okay.
the
Now
pixels.
here you have 5. And I'm
Yes.
adding 1 pixel here, 1 pixel here.
Yes.
So 5 plus 2 will be 7.
7.
So what is the size now? 7 by 7.
7 by 7. Yes.
If I take 32 by 32 image, if I pad it by 2, padding equal to 2, that means I'm going to add 2 pixels on this side, 2 pixels on this side. 32 plus 2 plus 2. 2 on this side, 2 on this side. 32 plus 2 plus 2 will be how much?
It's 2 to 4, 6, 36.
That is all I've done it. That is all I've done. And here also I'll add 2 pixels. Here also I'll add 2 pixels.
Yes.
2. 32 plus 4 will be 36.
Yeah, now I understand. Yeah.
Oh, yeah.
Thank you.
Yeah. Okay. Now, before I come here, I think there is this part which I forgot to cover to you guys. Cover, right? So let me explain this part. So if you have a filter, and if you have values 1, 0, 1, 0, 1, 0, 1, 0, 1, and if I have this 5 by 5 image, right? This image is 5 by 5. 5 by 5 is 25. So in the input layer, you'll have 25 neurons. Excluding bias. Bias also will be there. I'm not including it. And if you have a 3 by 3 filter, 3 by 3 is 9. You'll have 9 here. 9 what? Neurons. Now, what are we doing? We are first applying on this patch. When you apply on this patch, that is first row 3. 1, 2. To get a single output, what is it that we are doing? Here, you want a value, right? So 1, 2, 3. Then for this, from the second row, you're taking 3. 1, 2. Then for this third, for the third row also, we are taking 1, 2. And what are the values? The 101, 1010, then 101. Okay. Then if I'm say applying on this patch, then this third row, which is this, would get this value for you, 1. So you have 2, 3, 4, 5, 6, 7, 8, 9. So you have all those 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 neurons. 1, 2, 3, 4, 5, 6, 7, 9 out. Okay. Now, if you want to get this 2, which is probably this position, what you do is take this third row, 3. 1, 2, and then take this row. 1, 2, and then take this row. 1, 2, 3. And here, what values will you have? 8 values. 1, 0, 1, 0, 1, 0, 1, 0, 1. The same weights are getting repeated here, here, and on every other patch that you apply, the same weights are, or the same parameters are getting repeated. So weights, all these are called as weights or parameters. The same weights are getting shared across, no matter how many or what is the size of your input, the number of weights that your model is going to learn when it comes to convolution neural network is equivalent to the filter size. Plus, of course, bias. Bias also will be there, 1 to all these. But then I'm ignoring bias just to explain the concept first. So 1, 0, 1, the same weights are going to get repeated across. So how many weights is your model going to learn in this particular example? 9 weights. So the weights are getting shared. So within CNN, weights get shared. And remember, we had a problem in multi-layered perceptron. The number of parameters are large, but the number of parameters now for us became very small. Became very small. Only that is equivalent to the number of, or it is equivalent to the filter size. Wonderful. And you are not processing the entire image. Every output in a multi-layered perceptron, every neuron, each of these 25 neurons will be connected to this. All the 25 neurons will be connected to this. All the 25 neurons will be connected to this. In that way, it happens, right? But here, that is not the case. Only on this patch, you are applying this filter only on certain patches of the image. Only those patches are taken forward. So you're not wasting, you're not giving equal importance to every pixel. In MLP, every pixel was given equal importance. Here, you're not doing that. Here, you're focusing on the local patches. So MLP focuses on entire image, global. CNN focuses on the patches, so the local regions. The amount of compute processing which is needed is going to be much less. Okay. Given that explanation, we are here, number of parameters. If the filter size is 25, you'll have 25 weights, parameters, and you have 10. 25 you have to also include one bias, so you'll have 26, and then 26 into you have 3. If you apply 5 by 5, since you have depth 3, you'll have size 5 by 5 by 3, plus you'll have one bias. So overall you get 76. And you have 10 such filters. So 76 into 10, which will be 760. Since input image has 3, you get 3 plus 1 is for your bias. And then you get total 76 parameters for each filter. You have 10 filters, so multiply it with 10 and you get 760. This is the same thing which is explained in math format. We discussed, if you have padding, then the formula changes. If you don't have padding, it is n minus f divided by stride plus 1, right? In this n, if it is 5 by 5 image, then it is width into height. So what you can do is this formula can be written as 2 parts. One is width, one other is height. So you can write it as W minus F divided by stride plus 1, height minus F divided by stride plus 1. But if you do padding, what will happen is if you have 5 by 5 image, if you pad it by 1, you say pad equal to 1, you add 1 pixel around. So 1 pixel here, 1 pixel here. Ideally, 2 pixels get added, right? 1 here, 1 here. So it becomes 7. And here also you'll have 1 pixel, here also 1 pixel. Again, 5 plus 2 is 7. So if you also want to include padding while you calculate, do the calculation, you just say plus 2 times of padding, because if you pad it by 1, then 2 pixels are getting added. Plus 2 times of padding, plus 2 times of padding. And that's a formula which is given. It's just a math representation, nothing much. Right? So this part I'll remove. This also we spoke. Okay. So you have conv relu, pool, conv relu, pool. You understand all these things. And then you have a fully connected layer. But pooling layer is getting added additionally. What is this pooling layer? We need to understand what is a pooling layer. So you have this image and you're applying a pooling. Pooling will actually downsize or downsample your image. When your image becomes small, it will get processed faster. Okay, processing becomes fast. Sorry. Okay. And when it comes to pooling, you have max pooling, average pooling. There's something called as global pooling. Max pooling means if you say I want to have a pooling layer of size 2 by 2, then if this is your image, 2 by 2 means, and say you're also saying I want to stride by 2. So what you're doing is you're taking 2 by 2. You can put stride equal to 1 or stride equal to 2, stride equal to 3, obviously. Stride equal to 3 on this, it won't be applicable, but stride equal to 1 or 2 works. If you say stride equal to 1, then it will first apply here because you're saying pooling layer with 2 by 2. And since it is max pool, you take the maximum value out. What is the maximum value? 6. Then again, if it is stride equal to 1, it will move like this. And it will pick the maximum value. But since you're saying stride equal to 2, you'll move here. and then you take the maximum value. Then stride equal to 2, you get the maximum value. Then stride equal to 2, you get the maximum value out. Okay. The advantages by doing this pooling. Okay, you also have average pooling, right? If you do average pooling and 2 by 2, then you take all these values and take an average of that. So it'll be like 1 plus 1 plus 5 plus 6 divided by 4. So it'll be 13 by 4. Whatever number you get, that number you put it here. It will be around 3. Average pooling. And stride equal to 2 means move it by 2 pixels and then do the calculation. L2 pooling means if you're doing L2 pooling of 2 by 2, you apply on those. And stride 2, okay? So L2 means you say square. 1 square plus 1 square plus 5 square plus 6 square. Okay, you square all these values and then take a square root of that. Whatever value you get, you put it there. One second, sorry. Okay, that's how you calculate for every patch. Okay, and then the advantage is that when you have image translation, meaning if you have an aeroplane image like this, or if you have an aeroplane image like this, or if the aeroplane image is rotated like this, or like this, or like this, in whichever direction you have your airplane image, it will identify that that is aeroplane. Maybe you trained your model only on these images, only on images where aeroplane was like this, straight. But while you were testing your model, aeroplane image was like this, looking upwards. Still, it will classify that that is aeroplane. Why? Because you have actually done some kind of pooling. Okay, that's the use of pooling layer. This already, pooling layer does not learn any new parameters. There will not be any new parameters that will be involved. And it doesn't impact anything. The formula is again n minus f divided by stride plus 1. This formula does not change even if you do any pooling. So you do con Vrelu pool, con Vrelu pool, con Vrelu pool. You learn all the features from your image and then give all those features as inputs to your fully connected layer or multi-layered perceptron or dense network or MLP, whatever you want to call it, and then it's going to give an output. Say it's a 5-class problem. That means you have 5 classes. You need to classify what is this image. For each and every class, it will give you the probability values as output, and you choose that which has the highest probability. Okay, and here is AlexNet example if you are interested in, right? AlexNet, Alex Krzyzewski in 2012, he and his team from University of Toronto have experimented a lot of things, and they could somehow come up with this, that they use 96 11 by 11 filters, stride 4, no padding. Then they use max pool, 3 by 3, stride 2, then normalization layer, then con, then pool. They tried out experiments, friends, simple. They try to use ReLU activation functions. They use some kind of batch normalization, data augmentation, dropout, batch size was 128, SGD momentum, learning rate, L2 decay, 7 ensemble techniques, and then eventually they achieved the accuracy that they have achieved. The point is, there are a lot of people, lot of universities, lot of colleges, lot of researchers who are experimenting with a lot of combinations. And any combination which actually wins a good, if it wins some competition, people are following that. I mean, if AlexNet has one competition based on this architecture, I'll use the same architecture for my business problem also. Why do I need to again experiment? If you want to use the same architecture for your business problem also, then that means you're making use of pre-trained model. Already it is trained, you're trying to make use of that. Okay, so that's how it is. Of course, we have already spoken about all the practical issues. All right, and then that marks the end of CNN. So in the next module, we will run CNN code hands-on. Of course, we will use first TensorFlow, Keras combination. Then we will also run this code using PyTorch. Once this is done, we would get into theory of RNN, and the same logic continues. We will do hands-on, we will run the code on both TensorFlow, Keras, and we will also do the same on PyTorch. So we will do it tomorrow at same time. Okay, thank you so much for attending, and have a great day ahead. Thank you all.